Now we start recording. Has both? But where were the actual vectors in that movie? Well, Robbie, I wouldn't say you were wrong, because technically anything that had any motion could show vectors or could illustrate vectors, but specifically the roller coaster, because what are vectors? This little notation, well, not little notation, it's actually kind of big, but as you can see right down here, a directed line segment, that's another way of putting it, if that helps. A directed line segment is what some people would say. Wait, line segment, what is that trying to warn you about? Why is it saying line segment? It's part of a line. What else? It's referring back to geometry and trying to warn you about something. Directed line segment. Tony's almost there. He said only one direction. And this vector does only go one direction. You can only, with each individual vector, well, that's going to get confusing a little bit, but in general, only one side is directed. But in geometry, what was a figure that only went one direction? It wasn't a line segment. It was a ray. But what's true about a ray? It has a beginning point and it goes on forever. What is this saying? Not forever. So it has a length, and the length means something. It has that length. Some people would, when they're introducing vectors, would actually show a point at the beginning and a point at the end with an arrow at the point, showing that you're going this direction, but you still have a finite length. So directed line segment means there's a length to it, and the length is important. Some vectors will be small, some vectors will be big. I'll show you illustrations of that in just 1 second. But this is not a ray. This does not go on forever. The actual lengths represent the measurement of that line segment, which could be a length, which could be like meters or feet or miles, but it could also be a force, a velocity like feet per second, mile per hour, centimeters per second, a force like meters per second squared, ooh, feet per second squared, ooh, what's a really common measurement measured in meters per second squared or feet per second squared? 9.8, 32, 9.8 meters per second squared, 32 feet per second squared. Nobody from physical science? Isaac Newton, apple on his head? Gravity. Gravity is a force. Wait, is gravity a force that is to be reckoned with? No. No? It's not a force to be reckoned with? We don't really need to worry about gravity? It's not a big deal? Yes. Jason, here you go. Come on back. Here you go. Gravity. Force to be reckoned with. Look at that. Anyway, coming back. A couple illustrations before we get too much further into vectors. P.S. Vectors could be like a whole chapter in physics, hence why section 6.3 is going to take us a little bit of time. 6.4, a little bit more time, but not too much. 6.3 is the main foundation for vectors. 6.4 is a little bit further application. 6.5 says, hey, guess what? All the work we just did somehow applies to complex numbers. Random, but it does. But real quick, what do you guys notice in these diagrams? We would call them vector diagrams. This would be a vector diagram. This is just a scenario. First of all, what's going on if they're on loops? Roller coasters, good. There is a lot going on, but where are the vectors in the roller coasters? And the forces acting on the car. And you could also say the people in the car, but we're just going to use the car as an example. Because for a vector diagram, we really want like a center of gravity that we're dealing with. So even though we could be talking about all these individual pieces and what the forces are on all these different edges, etc., and on the person themselves, we're just going to be talking about the center of gravity. So just talking about like the center of the mass of the car. So acting on the little center of the mass of the car, what do you guys think this guy is? And what do you notice about all the gravity forces? They're all pulling down, right? Is that a big deal here? Is it a big deal there? Is it a bigger deal there? Yeah. However, there is something called centripetal motion, and that's this whole other beast. You guys know centripetal motion, right? Besides the country song, if you're into country. It's an old country song. What's centripetal motion? How do you illustrate it? Did anybody ever do it in physical science? Why am I doing this? Yeah, but my arm isn't that exciting. What's the illustration? Have you ever seen it? Maybe your teacher was too scared to do it inside. They might have done it outside. Water in a bucket, and if you spin it really fast, theoretically what happens? It stays in. What? No. Pour the bucket, the water spills out. But centripetal motion. It's not magic, it's science, yeah. Maybe all science is math. Anyway, all life is science, all science is math. That's a very simplified form. But coming back. So, not going into centripetal motion too big. We're not like going all into physics and just going to stop doing math and start doing physics, although maybe physics is math. Gravity goes straight down. Now hold on, what do you notice about gravity in the other vectors? Are they the exact same lengths? Are they the exact same lengths? Doesn't really look like it. Doesn't really look like it here, right? It doesn't exactly look like it there. So seemingly there's a little bit of differences in the actual lengths themselves, but you do see other words besides gravity. What are the other two that you see? Norm. Anybody know what normal? That's okay. Norm for normal. Normal. Any idea what it means in physics? Have we used it yet this year? Normal. If you just want to make yourself a little side note, you're going to see it maybe once or twice this year. In physics, you would see it more. In calculus, you would see it a few times, although calculus kids always forget it when we get there. Normal means perpendicular, aka hitting it at 90 degrees. Wait. Degrees to gravity? Doesn't look like degrees to gravity to me. Does it to you? To the motion of the car. You guys see it? Where's the car going? 90 degrees. Where's the car going? 90 degrees. Where's the car going? 90 degrees. That's a little bit off, but I just wanted to show you it's not exactly gravity. Where's the car going? See it? Now wait, is the car literally going that way? Oh, I hope not. We're all going to die, right? The car's not literally going that way, so what do I mean? The car's going that way? No. Although in some of these it actually is. But at this moment, the force, the combined forces of the car, as far as the motion of the car, if you were to take away the track right here when the car comes up, what would it do? Right? We call that a trajectory. If you guys have watched Hidden Figures, the trajectory of the rocket or the trajectory of the entry. Trajectory is if you were to, what's a good example? How about like, not shot put, how about discus? You guys know what I'm talking about with discus? It's an Olympic sport, it's a track sport. When you spin, 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 and what do? You let go, right? That's the trajectory that it's on. So if we were to take away the track, you can think about what the normal force is normal or perpendicular to is where the car would go if you were to take away the track. Where the car would go if you were to take away the track. Anyway, coming back. So there's normal, but what's the other word that you see? Net. We've seen net this year. As far as like a mathematical term, not, I don't know, basketball net, not like that. Where have we seen net? It was in businessy applications. Net worth. Yeah, that's one way. That we haven't actually talked about it, but net worth, someone's net worth. Or in like a business, their net gain, profit. What does the word net mean? Net worth, net profit, net gain. Kind of like total, including everything, taking all things into consideration, right? So net is kind of like putting it all together. Well, wait a minute. How does this put all this together? How does this put all this together? How does this put all this? Oh, actually, this one kind of makes sense. How does this put, okay, hold on. How does this one make sense? It's a sum. And the vector sum is easy because they're both going in the exact same direction. So take this one plus that one, you get that one. That's easy. It's like segment addition. You see it? So green plus blue. or gravity, the force of gravity plus the force of normal. It's really easy when they're in the same line as each other. When does it get hard? Look at the other three. When they're not working perfectly in unison, perfectly in line with each other. Now, hold on. Hold on. The reason you don't die on this one is because, well, first of all, shoulder harnesses. But second of all, maybe a lap belt, but usually shoulder harnesses. But second of all, because of all these forces that are working as you get up to this point. So these are important. Does anybody see anything in common about how this little net guy, I'm going to go ahead and throw this over, net. You can think, just like a really simple way of saying it, you can say combined. Or like the overall effect, putting everything together. There's a few different words that might help you get the idea of net without getting too technical. But do you see any similarities about how the net force is drawn? Where it's drawn from to in these three diagrams? Because these are totally different nets, right? But how are they in green? Do you see any? Okay, they're all forming triangles. Are these all right triangles? So why do you think we did law of sines and law of cosines right before all the physicsy stuff? We're going to have oblique triangles. Maybe, if we don't like the oblique triangle, maybe we could do some right triangle action out here and make it easier? Anyway, too hard, too much, too soon. But we're going to have oblique triangles, and maybe we're not going to like the oblique triangles sometimes because of bearings, basically. So maybe we'll do some right triangle stuff, kind of sneaking it off to the side. But yes, we're going to have oblique triangles. So yeah, they all form triangles, but what else is anything in common? They start at the beginning of a vector, and they end at a... Oh, they start at the beginning of one and end at the end of another. So in a sense, are we kind of like flowing through the entire situation with the net? You flow through the situation with the two separate. When you're adding two vectors together, it says, okay. Does that make sense? The overall. You flow through, what's the overall effect? You flow through, what's the overall effect? And net force, you flow through, what's the overall effect? So when they're in line, it's easy, it's just a line segment. But when you have forces that are at any sort of angle, you're going to be forming a triangle to get the net force. Now, here's a question. What if I was to give you an example of a vector? Oh, hey, roller coaster. Yay. Except I don't like this one because do you see how gravity looks like different lengths in each of them? Is this a very technical picture? No, it's more of like, oh, look, stuff's happening. This one's better, much better. But let me just kind of introduce one more idea. What if you had a hill? Let's just call it an inclined plane. What if you had a hill, but I'm going to be like a really boring hill. It's just going to be like an incline. So we can think like a skateboard ramp or something. Even that would be usually curved, right? I don't know. A really boring skateboard ramp. Okay? And that transition would be kind of rough too. Anyway, we have a ramp. Okay? Let's say there's an object on that ramp. And we're not getting super technical. Talking about friction, we're not going crazy with friction. We're just not ready for it, and we're not a physics class. We're pre-calculus, pre-everything future math, which might include physics, and might include statistics, and might include probability, and might include business, and might include calculus, and might include physics, and might include linear algebra, and might, Okay, there's a lot of things math applies to. And chem, and bio, and. But there's a box on a incline, okay? And let's say you're trying to push said box with a certain force. Let's say you're trying to push said box with a certain force. And let's say you have gravity acting on it, going straight down. There's actually a force of the box against the incline itself. Oh, stink. There's actually a force of the incline itself. And then we could technically talk about our normal force also. Do you guys see a dilemma that's starting to happen? How many vectors do we have? Can there be more than 2 vectors acting on a situation? So how do we add more than 1 vector? Now, I'm not going to actually use this situation right here, because technically, to be honest, I wouldn't have put the xy axis there. I would have put it at a tilt right in here. Do you see it? I would put the xy axis right there. In physics, we start moving around the xy axis. So let me go ahead and take away the situation. And let me instead just kind of do, okay, what if we were to talk about this? What if, going away from forces and using the other, look at your notes. What else can a vector be used to note? Force or velocity or even just length? What if we were talking about another situation, like a boat that starts from a certain port and goes out a certain bearing or a certain direction for a certain amount of time at a certain speed? And then what if we say, oh, hey, he sees something cool over here and he backtracks a little bit at a certain speed, slowing down, trying to find, I don't know, the whales or the dolphins or whatever he saw over there. And then he was like, oh, yeah, that's right. I'm supposed to be getting over here. And if this was the actual course of the ship, and let's say it was pretty on cruise control, then on cruise control, then on cruise control, just to make it simple, as soon as you start saying that there's varying speeds, life gets a lot more complicated and you actually need calculus, so we can't really quite do that. So we're going to say constant speed, constant speed, constant speed, even though in your head you realize you had to speed up and then slow down. Hopefully he slows down in making that turn, otherwise we're in trouble. People are flying off the boat everywhere. But let's say he realizes that he has someone who's sick and the medic is way over here, and then they know where they're going to end up and they're at this other port. They're trying to get in. Family's trying to rush to see them. What bearing and at what speed should a ship leaving here take in order to try to meet them over there? That's one way of thinking about it. Another way of saying the net force. The ship went there, went there, went there. The net force would be like, oh, hey, I'm trying to get from here to here. Is that a nice, pretty triangle? How do we add those vectors together? Let me make it just a little bit prettier so it's not quite as gross, because you guys see how the red is like cutting through my entire diagram. That's kind of sad. Net doesn't always mean putting all the forces together. Net might just mean putting all the journeys together. There we go. That'd be a little easier. What would you need to know to be able to get from here to here? Like how long? Oh. Kim's saying we could make triangles like that? We could do like here. That's going to be an awkward cut though, huh? We could do here, but that won't be the right angle. This is the net, yeah. It's a little baby net. Do you guys see what she's talking about? Couldn't you take this guy and say, oh, overall, that's what just happened? And then couldn't you take this and then take this? And then that? So maybe we could use these two. Maybe we could use the angles somehow with geometry to go ahead and figure out this length in this triangle. And then we could figure out that triangle. Do you see all the obliques going on, though? And if we have to use law of cosines and law of sines, does that seem messy? What would we rather these triangles were? Good. What would we rather these triangles are? Right triangles. Wait. if they give us a direction and a magnitude, and figure out how far over and how far up. And then if they give us a direction, now this might be a little hard for some of you, but from this point in space, a direction. Couldn't we technically make a little right triangle and figure out those ones? And then if they give us a direction and a magnitude, for right triangles, all we need is one angle and one side. And then we could figure out x's and y's. And guess what we could do with all these x's and y's? We could say this x minus that x plus that x is going to end up equaling what? This x. So if we take a1 minus a2 plus a3, guess what? We get this length. Guess what we could do with the y's? This b1 plus this b2 plus this b3, and we could get? And what can we do if we know this one and if we know that one? Oops, don't know where c came from. Can't we just do a squared plus b squared is c squared? Pythagorean theorem. Couldn't we do tangent inverse of b over a to get my angle? And I didn't have to worry about these nasty obliques all along the way. I said, forget that. I'll take you one at a time. Who's your x? Who's your y? Your turn. Who's your x? Who's your y? Your turn. Who's your x? Who's your y? X's? Y's? Got 'em, coach. Something called linear combinations. Guess what? We pretty much just covered all of section 6.3. But maybe we should practice some of it. Magnitude. There's notations, there are formulas, there are all sorts of things, but almost everything, this section will come back to something from a triangle that you've already seen. We're just applying it, whether it's right triangles, whether it's oblique triangles. But there are some things, especially like magnitude, direction, notations, that we need to talk about. So you've seen a lot of complicated stuff as a humongous introduction for what we're about to start breaking down piece by piece. A vector is a directed line segment. A segment has an actual length, and we call that length its magnitude, its greatness. The magnitude of an earthquake. We live in California. You've heard that before, right? Magnitude, the how muchness. But magnitude is not just in terms of earthquakes. That's just the one you guys usually hear it in. But magnitude could be like, how fast is it going? Magnitude could be like, hey, what's the force? Oh, that makes sense with earthquakes. Magnitude could technically just be like, how long is it? So the length of the segment literally stands for the how muchness, or much better, the magnitude of whatever the vector is measuring. And as you guys notice, notation for magnitude, it looks like double absolute values. Do you see it? Double absolute values. Now I'm going to go back. I'm actually going to dual page to that vector that I wrote down just a second ago. You guys just drew a very basic sketch. Let me show you a couple things. If the vector's name is PQ, do you remember how in geometry the order of the points were kind of important? Especially with like array. It's not array, I know. It's a directed line segment. But it's still important here. Which point do you guys think I'm going to measure P? The beginning or the ending? The beginning. We call that the initial point. And you can tell it because isn't it at the beginning of your vector? Who's the ending point? Q. And if it's something like gravity, it's not like, oh, gravity starts here and stops here. No, it's just the direction and the force behind it. But if it's like a ship that's going a certain direction at a certain speed, well, yeah, it might be the beginning and the end. So P we would call the initial. We can also call it the tail. Think tail of a comet. Q we call the terminal or the final. But we could also call it the head. That's a much better way of talking about it. Think here's the head of the comet, here's the bright part, and here's all the stuff behind it. So we actually talk about heads and tails of vectors. If you guys notice, and you might not have noticed at all, but do you notice I totally skipped over this little notation right here? Illustration of a vector, and then I put comma, and I put V or, now hold on, is that a normal V? Those don't look the same. That's a bold letter. Here's the struggle. Guess what your book can do because it was using a word processor? Make things bold. Guess what you can't do because you're not typing. And I don't want you to try to be like, it's bold. No. So when we're handwriting vectors, even though the book is going to show bold letters, even though the answer key on CalcChat is going to show bold letters, I don't want you showing bold letters. Even though the questions are going to show bold letters, I want you, any and every time you write a vector, to put the arrow above. So yes, it is going to be a bold letter, but you're going to write the arrow above. And you could just name it like one single lowercase letter, like V. Or you can use the 2 points, the initial and or the head and the tail. You can use the 2 points as well. Now you could use a little double-ended arrow. I actually don't like doing that because in geometry that is a ray. I do a little single-headed arrow. It still gets the idea. You still know it's going a certain direction. It's kind of more physicsy, a little bit more. I don't know. At least that's how I did it in college. Just a single-headed, but it technically is a double-headed arrow. But I just do a little single one. I think it looks cooler and it's a little bit faster and it doesn't get as easily confused with a ray. But if this is true, I want to start introducing you guys to the idea that every single vector can get broken down into a right triangle where we could theoretically figure out the A and figure out the B. There's actually a lot of geometry that could help us with that. Or I should say trigonometry, especially if we have the angle, the direction, and if we have the magnitude. Now we know the notation, the double lines. Then we have the hypotenuse. This is an actual length. Then we have the hypotenuse, then we have the theta, and we can get the A and B using right triangles. And we'll do that. We'll write down the formulas for it, even though it's technically just working with what we should already know. But long story short, we can find the magnitude, or it will be the hypotenuse, which means we can solve for him like we solve for any hypotenuse, a squared plus b squared if we have it. A squared plus b squared if we have it. Or if we have the hypotenuse, okay, we can set the hypotenuse equal to square root of a squared plus b squared. The other important concept on this page is equal vectors. If you guys noticed on that roller coaster example, I pointed out the fact that all the gravities look to be the same length, right? And the reason why all the gravities look to be the same length is because, does gravity change based on the object it's acting upon? No, gravity stays the same. Now, does the mass of the object make a difference as far as how fast it falls? Possibly, take physics. But coming back, gravity's force doesn't change. Wait, so that's equal to that, equal to that, equal. Yeah, they're all equal vectors, but they're in different places. Yeah, but they're the same length, and they're going the same direction. So actually, over here, when you guys look at these vectors, I copy and pasted them all. All of them came from one. If I copy and pasted them all, what's true about all of these? Even though they're in different places, like if I was an X and Y graph, even though they're in different places, guess what? They are all equal in the eyes of physics. Jason and Aiden, go ahead and stand up. They're all equal in the eyes of physics. So the location, as far as where it's at on like some sort of grid, the location has no bearing, has no impact on whether or not they're equal. What they need is to have the exact same angle from a horizontal, or exact same angle from like north or south or east or west, the exact same direction. And be careful, if an arrow is going in the opposite direction, it's an opposite vector, not an equal vector. But the exact same angle and the exact same length, but it could be anywhere in the picture. I would still say they're completely equal. So if you guys get to a few examples, let's do this one. How could we show that these two are equal? if we have the ordered pairs, we need to be able to show that the angle is the exact same and the length is the exact same. How can we find the length of these vectors, guys? Just using the math that you've learned. Distance formula. Yeah, that's one way. Does anybody remember that there was an easier way to the distance formula that I tried to point out to you a long time ago? Jason Stand. Thank you. You could do x2 minus x1 squared plus y2 minus y1 squared with the square root, but who remember that perfectly? Like half of you. What's the other way? How long is the adjacent side? 3. How tall is the opposite side? 2. How do you know that? Well, because you went from one point to the other, right? The x to the x and the y to the y. Now what can you say? The magnitude of u is equal to, isn't it just square root of 3 squared plus 2 squared? What's square root of 3 squared plus 2 squared? Well, root 13, right? What would u's angle be? Well, if I have an opposite and I have an adjacent, how do I get to a theta, cool kids, of a right triangle? Tangent inverse. I can say the theta of little vector u is going to equal tangent inverse of 2 over 3. I could plug that into my calculator. How about for vector v? How far over? Do you guys already figure out it's 3? And it's 2? Now we could do the math to that, but it is 3 and 2, so guess what? Vector v, with some simple math, is also going to be root 13. And what's theta v going to be? Tangent inverse. I don't even need to plug it into my calculator. Can't you guys tell they're equal? Now hold on, pause really quickly. There's going to be a lot of u's and v's. Pause. One thing. If you guys are writing this picture, did you put little arrows above u and v? If not, you're wrong. You got it. You can't use the bold. You have to use the little vector notation on top. So if you're writing the picture, write your little arrows. I'm going to do it whenever I write, but if it's from the book, it's going to have a bold letter. Put your arrows on top. And number 2, how many of your u's and v's look very similar? Look at your notes. If your u's and v's look very similar, this isn't going to cut it. Put a little tail on them, please. Please, please. Put little tails on your u's or else I'm going to get really sad really fast. Wow, we did a lot of vectors, but very little notes. Guess how much of homework you're ready to do? Probably not too much. What didn't we get to do? I don't know. Let's see. Component form. Something about component form. How to add and subtract and multiply and divide vectors. Who these little i's and j's are. Something about angles, and then word problems. Now, does that look like 3 days worth? Maybe, maybe not. But it definitely is more than today, right? But do we have a good intro? Get out of here. See you guys in chapel. Bye. If you need inspiration, watch Despicable Me, but don't ignore other homework because math's going to get harder as we go. Toodles.